Hello and welcome to Software Architecture course. In this lecture, we will talk about performance, one of the important quality attributes, and what are the tactics to basically address different performance related requirements. So first start with the basic concept of performance. What's meant by performance? Performance is something that most of the architects have been dealing with in their career, and this is one of the most popular quality of service. But sometimes we also do not clearly understand what's called performance and what is not performance. So essentially, let's look at the definition. The definition is that software system's ability to meet the timing requirements when it responds to an event. So that's what is called the performance. Performance means that when there is an event that comes to the system and system is supposed to respond to the requirement, it must respond within a certain time. And if it can meet the timing requirement, then then we can say that its performance requirement is satisfied. So these events could be interrupts, it could be messages, it could be requests from users or from other systems, or it could or there could be some clock events that can mark the passage of time. So events could be either coming from outside, like interrupts, messages, requests, and so on, or it could be clock events coming from within. So the most important part is that the system or the part of the system must respond to this event in time, because if it is not if it does not respond in time, then we say that its performance requirement is not met. So just responding to the event is not enough, it must respond in time. So earlier we introduced different scenarios, quality attribute scenarios, which are essentially the way to capture requirements. So let us now look at how you can capture different performance scenarios or performance related requirements. So as usual, we start with the users who is basically generating this stimulus. It could be external or it could be internal. One example is it could be users. So here what I have shown here is that at the bottom is basically the example, the users. Then the set of stimulus that the system can respond. So essentially the stimulus are nothing but events, which could be periodic, which could be, let us say, sporadic, it could be stochastic. And one example is that user submits transactions and expect response in 3 seconds. So that could be an example of stimulus, that it is submitting transactions. Now what gets impacted? Essentially it is typically the entire system that would be impacted. And what is the context? The context is that the system, when system is either running in normal mode or in the overloaded condition, in both these situations a stimulus can come, and then the system has to respond accordingly. So what are the mitigating actions? Mitigating actions are the system processes event in time, or the system can change its service level. Both are allowed mitigating actions. So in the example that we were saying, so the user submits transactions and it expects a response in 3 seconds. And in this example, the system is running in normal mode and the transaction is processed. An example is that the average latency is 2 seconds. So what are the measurable response for the performance scenarios? The measurable responses are latency or deadline by which it must be processed, or it could be throughput, which is in terms of number of events processed per unit time. It could be jitter, it could be miss rate, or it could be even data loss. So these are all measurable response that are allowed. So when you are capturing the performance scenarios, remember that you are capturing performance requirements as scenarios. In that case, you can use this as a template and capture the specific requirement. Example is that you can capture a requirement like user when submit transactions, and the user's expected response time is 3 seconds, and the entire system is impacted, and when the system is running in normal mode, the transaction will be processed with an average latency of 2 seconds. That is a very concrete requirement. Okay, now changes in service level is obviously due to overloaded conditions. We'll talk about that later. So let's look at events and responses in a bit detail. So event, it could be periodic. It means that it can come at a regular intervals, like real-time systems. It can come at regular intervals. Or it could be stochastic. It can come randomly following a probability distribution. For example, e-commerce website, the requests come randomly, but with a particular probability distribution, for example Poisson. Sporadic is that you really do not know when it's going to come, and it can be really modeled either stochastically or periodically. For example, a keyboard event from a human. And there are different types of responses. The responses could be, one could be latency. The time between and the way the latency is measured is the time between the arrival of the stimulus and system response. That's called latency. And throughput means the number of transactions processed per unit time. It typically could be second, could be hour, could be minute. And jitter means that what are the allowable variations in the latency. While latency is the time, what is the allowable variation? In the previous example, the latency was 3 seconds, and or rather the average latency was 2 seconds, and the variations allowed maybe plus minus 0.5 second. Even number of events not processed, that could be a miss rate. So when the system is in overloaded conditions, then even the measures could be the number of events that have not been processed. So now let's look at different types of performance tactics that as an architect you should use to handle different performance requirements. So the first category is called control resource demand. The second category is called resource management. And the third category is called the resource arbitration. So under the control resource demand, the one tactic could be the reduction of the resources that are required. Another tactic could be reduce the number of events. Another tactic could be control the resource usage. Under the resource management category, there could be tactics like one can increase the level of concurrency. One can maintain multiple copies of data or computation so as to improve the performance. Or there could be another tactics by which one can increase the resource. In the resource arbitration technique, there could be different scheduling policies like FIFO, first in, first out, or there could be various other scheduling policies. We will look into these tactics in details. So under reduction of the resources required, how you can do it? You can basically reduce the resource consumption by actually increasing the compute efficiency, or you can reduce the overhead. Under the reduction of events, you can actually manage different event rates, or you can control different sampling frequencies, which will also reduce the events. Under controlled resource usage, one can bound the execution time, or one can bound the queue size, which can actually bound the number of input requests. Under the scheduling policies, it could be static or it could be dynamic, or it could even be a fixed priority. So let's look at a scenario, or let's understand in detail why system fails to respond. Well, the system fails to respond when the resource consumption is quite high. For example, by resource it means CPU, memory, data store, or network communication. A buffer may be sequentially accessed in a critical section. That might cause a delay which is unanticipated. There might be a workflow of tasks of which one of which may be choked with a request, and as a result the entire workflow is choked. There could be reasons like blocking of computation time. So there could be resource contention. There might be many demanding computation units, typically threads or processes, who are trying to access the same resource and thereby causing a contention. Availability of a resource might be an issue, because of which the computation time is blocked. There could be deadlock due to dependency of resources. So that, because of that, the system might fail to respond. So let's look at these tactics in detail. Controlling the resource demand. So one is increasing the computing efficiency. So what does it mean is that one can actually use a different algorithm, a better algorithm, for performance critical areas. One can reduce the overhead where the resource consumption is reduced, in fact, when it is not required or when it is not really necessary. So by that what I mean is, when it is not necessary, one can basically take a different technique. Example is that if you are dealing with distributed systems, and you know that the two of your objects that you are going to use and who are going to communicate very heavily, they are actually local objects. But when designing the system, you have thought of most general scenarios, and you have used more distributed communications. So distributed communications are typically used in RMI, using RMI, remote method invocation calls. Now, because and obviously RMI takes more time, consumes more time. Now, if you know that these two objects are going to be in the same machine, then you can use local objects and you can use local interface instead of RMI. Thereby, you can reduce the resource consumption. So that really requires the architect's decision. So this is what is called the designer's choice or architect's decision, to use local interface as opposed to distributed calls. Then remove of intermediaries. What that means is that oftentimes if A wants to talk to B, then there might be a mediator or a proxy or something like that, which takes a request from A and then gives it to B, instead of A making a call to B directly. So that obviously causes performance bottlenecks or performance issues. So this overhead can be reduced by A calling B, but that can conflict with another quality attribute, which is modifiability, because modifiability essentially says that one needs to introduce intermediary to make it more modifiable. So in this case, one can choose to either ignore modifiability and give higher preference to performance, or they can choose to give more preference to modifiability over performance, depending on the scenario. Then another is tactic is managing the event rate. So managing is about controlling the event rate. If you have control, then don't sample too many events. For example, if your system is supposed to analyze the environmental data and then do some processing, then if you have control, do not sample too many events if you know that your system is not going to handle so many events. So don't even sample so many. Or it could be that sampling time could be controlled. So what that means is that suppose you don't have any control that of in terms of sampling the any data, that it just keeps coming to you. You have no control. You can't somehow reduce the source. In that case, what you can do from inside is that don't even register those events. You decide certain sampling time and let the system sample only periodically during that sampling time. So basically sample them at a lower speed. What that means is that you are going to reject many such inputs, and you have to decide as an architect whether to what extent you can reject the request and you can lose the request and you can still do the computation properly. Now bound is basically one can actually bound the execution time. This is a very common practice in many of these complex algorithms where the algorithms really does not terminate. It can go on forever. So in that case, one of the very common technique is, and those algorithms are typically approximation algorithms, which are essentially tries to find out some optimal solution, and many times the algorithms are terminated based on certain condition. Now one can basically decide how many iterations should this algorithm kind of continue, depending on either the data type, or it could be how close is the result with respect to the optimal solution, or how to what extent the results are varying. Depending on various criteria, one can decide to terminate it. So this is called bounding the execution time. Queue size is essentially it can control the number of queued arrivals. So therefore beyond that, if it arrives, if those events arrive till that limit, you are going to accept it. After that, you are going to reject the input requests. However, remember that the queue size and sampling time, managing events are slightly different. In a queue size, you first keep getting the requests, and when the queue is full, just throw the requests till you process till the queue is again have some slot. However, for the event management cases, events continue to come in a stream, and in a sampling time reduction, it means that you are sampling at a lower speed, and you are actually just dropping some of the requests in between. So let's look at the technique which is managing of resources with respect to performance. So one of the techniques is increase the resources of the infrastructure. So this is pretty trivial, an obvious solution, that if you find that your application demands more performance, then you can go for faster processors, additional memory, or even faster networks. Or you can increase the concurrency, by which you could basically design your system so that many requests can be processed in parallel, or process different stream of events on different threads. You can create additional threads to process different sets of activities and so on. Multiple copies is that so that computations can be performed faster. One example is that client server, where essentially you know, you could have multiple clients and each client can basically do different computation in obviously different client computation. So multiple copies in this case is basically multiple client copies. One can have multiple server copies also, which can receive many requests at a time, and that's very typical in kind of load balancing in a data center. Now, multiple copies of data is also another technique by which you can increase the computation, and one of the good example is basically if you are aware of Hadoop and data intensive computation called MapReduce. In that MapReduce scenarios, one can basically have multiple copies of data to improve the speed of computation. So Hadoop essentially maintains data copies to avoid the data transfer and improve the data locality, which in turn can impact the throughput. Resource arbitration is about the way the resources are scheduled to reduce the contention. So the resources are again processors, buffer, or network. An architect needs to really choose the right scheduling strategy for a resource contention. FIFO is one of the ways, or fixed priority. So in the fixed priority cases, one can use a domain specific logic, such as a request from a privileged class can get a higher priority compared to some other class of requests which can get lower priority. So this could be a fixed priority. There could be another technique called deadline monotonic, where the shortest job can be executed first. In case of dynamic priority, one can choose dynamic scheduling policies like round robin policies, where there are many requests and then they are each of them are given some slot, and if there are n number of jobs to be basically executed, or if there are n number of resources to be given to different processes, so they can be allocated in a round robin fashion, and then after a time slot it is given to somebody else. If you think about CPU being a resource, then CPU can be given to first given to job 1, then it can be given to job 2, then it can be given to job 3, and so on, and then when job n gets a CPU, then again it's given to job 1. Earliest deadline first, it means that the job which has the earliest deadline to complete can be given the priority to actually grab the processor and then finish the execution. In case of static scheduling, also it's also called preemptive scheduling strategy, where after a certain time that job is preempted and then essentially it is evicted, and another job is actually used for execution. So in case of resource management, essentially and resource arbitration, important part that you must keep in mind is that these are the scheduling policies that sometimes or many a times offered by the operating system itself or even by the infrastructure. So as an architect, it is highly unlikely that you will end up writing such arbitration policies, but you must be aware as an architect what are the arbitration policies possible, and depending on your requirement you have to select the right arbitration strategy. In terms of design checklist for a quality attribute, let's look at what are the design checklists that are required for performance. So as before, we said that there are 6 design checklist categories, like allocate responsibility, modules that can take care of the required quality requirement, management of data, identify the portion of the data that needs to be managed for this quality attribute, and plan for various data structure design with respect to this quality attribute. Resource management planning, how infrastructure should be monitored, tuned, and deployed during the quality to address a quality concern. It's just a repetition of what I said in the earlier lecture about what are the design checklists. Management of manager coordination, how different system elements they communicate and interact with each other, how you are going to do different bindings. Now let's look at the performance, and now let's see what it means when I say that allocation of responsibilities. So first one, you need to identify as an architect that what are the features of the system that may involve or cause heavy workload, or maybe the features which demand high time critical response. Identify which part of the system that's heavily used. So identify that, and essentially for these analyze the scenarios that can result in performance bottleneck, and essentially address that in the design. How to address that is again very domain specific. In this course of software architecture, it's not really possible to highlight that because it's really example specific, domain specific thing. But as an architect, you need to basically do these two things. First, identify the features which might involve or cause performance bottleneck, or the part of the system that's heavily used, and then while designing, you must design keeping these things in mind, and see whether the system can really be able to handle heavy workload, or to what extent it can handle. Furthermore, you need to find out and assign responsibilities related to threads of control, allocation of threads, deallocation of threads, maintaining of thread pools, and so forth. It may so happen that you might use some framework or infrastructure which can basically do all this thread management. In that case, at least as an architect, you need to tune the different thread control parameters. Assign responsibilities that will schedule shared resources, or appropriately select and as well as manage performance related artifacts such as queues, buffer, and caches. Here what it means is that you need to find out how or who is actually handling these artifacts like queues, buffers, and caches, for which are related to performance, and can you and basically plan for fine-tuning that. Examples are, if you first identify that which part of the system or which part of the infrastructure is dealing with input queues, or which part of the infrastructure is dealing with the cache, and then as an architect you can fine-tune those according to your requirements so that the performance requirements are actually met. Management of data. Now identify the data that's involved in time critical response requirements, which are heavily used or which are massive in size. So for those type of data, you need to determine whether you need to really maintain multiple copies of the data. Do you want to really have different types of cache mechanism to improve performance, or do you want to really partition the data across different machines to improve the performance? Do you want to really reduce the processing requirements for creation, initialization, persistence, manipulation, etc. for the data? Or whether do you want to add additional resources to reduce the bottleneck for the creation, persistence, etc. so that creation, initialization, persistence, manipulation, and things like that are not a part of your mainstream operation. Then management of managing coordination is also a very important thing in managing performance. Look for possibility of introducing concurrency, and obviously pay attention to thread safety. For think about event prioritization and even scheduling strategies. Things like check will this strategy have a significant positive impact of performance, and if so, only then use it. Otherwise, don't. So then also, so essentially concurrency or building a concurrent program is not easy. It can create a lot of other overhead, specifically in terms of you can introduce more bugs, more, and it can actually impact testability, modifiability, and so on. So therefore, be sure before introducing concurrency that it is really going to give you a significant positive impact. Otherwise, don't go for concurrency unnecessarily. Determine whether the choice of threads of control and their associated responsibilities can introduce bottleneck instead of improve speed up. Also consider different types of coordination mechanism across different processing elements, stateful versus stateless. Obviously, stateless is much faster than stateful, and that's more desired. Synchronous versus asynchronous. Asynchronous is obviously more fast, but if you are going for asynchronous communication, then you have to have additional mechanism by which you can guarantee the computation. Whereas in synchronous mode, the computation is guaranteed. By synchronous, it means that you make a call and then you wait till that call is over. Whereas asynchronous means that you make a call but don't wait for its response. Just you keep continuing in a different thread, and you expect that the processing element, which is processing your asynchronous request, once it is done, it's going to notify you. So these are the different tactics, or in fact, these are the different design checklists to manage the coordination. Let's look at the tactics. Let's look at the design checklist for resource management part. You can determine which resources in your system are critical for performance and ensure that they are monitored regularly. It's a very, very important thing, and that's what a lot of people do as a good practice, that after you deploy the system, you have to watch for different resources like CPU, memory, and monitor, and then manage it well. Plan for mitigating actions early. For example, when the heavy networking load occurs, determine whether, and if you find that that's what happens most of the times, in that case you can redesign. You can see if you can want to collocate some of the components so that the load on the network is actually reduced, or you can ensure that the components with heavy computation requirements are assigned to processors which has very high processing capacity. Prioritization of resources and access to resources is important, which means that scheduling and locking strategies need to be looked into, and locking obviously reduces performance, and you might want to basically remove locking in a judicious manner, so that while your integrity of the processing is not hampered, but performance is improved. Deploying additional resources on demand to meet increased loads. Nowadays, in cloud computing and in virtualized scenario, this is a very common case where you are adding new resources on demand. Typically, virtualized computation scenario, cloud is essentially that, where you can on demand get different virtual machines, or within a virtual machine on demand you can increase its capacity. Performance design checklist. We're talking about binding now. So one element can be bound after compile time. Basically determine the time required to complete the binding, and oftentimes if you go for dynamic binding, it causes an overhead. So the late binding, dynamic binding do cause overhead, and if you want your application to be really fast, you need to really analyze this dynamic binding and decide whether you really need it. If you don't need it, you should actually eliminate or completely avoid such kind of late binding mechanism. But the thing is that this late binding is a very popular practice, and that has a very good impact on modifiability. But late binding has a very negative impact on performance. But late binding actually has a strong positive impact on the modifiability tactic. technology choice is a very important factor for performance. So choice of technology is often governed by the organization, unfortunately. So those are basically the design decisions that you have no control over, and you cannot even argue. You have to accept it and then go forward. So find out, in some cases, find out if the chosen technology will really let you set and meet the real-time deadlines. Suppose you are dealing with an application which requires real-time deadlines. If you know the characteristics under load and its limit, you find if the technology chosen will really be able to really meet such requirements. Does your choice of technology give you the ability to set things like scheduling policies, priorities, policies for reducing demand, or allocation of portions of technology to different processors? Does your technology say that yes, some part of the computation goes to processor A and some part of computation goes to processor B? Do you have the control? So while selecting a technology tool, you need to look at these factors. Does your choice of technology really introduce excessive overhead? Obviously that you need to really look at and then see if that impacts the performance. So in this lecture we have completed performance, which is a very important tactic, which is a very important quality attribute, and we discussed various tactics that are used to handle different performance requirements. In the next lecture we will address other quality attributes. Thank you.